All right, so we made it to level 1.2, and you might be asking yourself, okay, we're spending a lot of time on these graphs of equations. Why do we spend so much time with that? Well, there is a ton and ton and ton of data out in the world. As you can see, I just pulled this from our book. You can see they had a table based off the years and the price of, adjusted for inflation, the price of gasoline in California. So what data and graphing allows us to do is to visualize trends that are happening around the world and around us all of the time. So this chapter and this section and this level is going to be focusing on the basics of graphing, finding intercepts, and we're going to talk a little bit about symmetry. All of this should seem familiar, so we're going to just dive right in. So first off, determining if the following points on the are on the graph of the equation 2x minus y equals 6. So in order to do this, to determine if these points are on this equation, we have to see if ordered pair yields a true statement. And that's a fancy way of saying, if I plug this in and I get 6 out, I win. It works and it's on the graph. So let's just try this out. 2 times 2, this is plugging in, minus 3 equals 6. So 2 times 2 is 4, minus 3. Does that equal 6? Well, 1 does not equal 6, so that's no good. So oftentimes when we do these, you'll see a question mark over the equal sign, and that's unsure if that's true or not. So let's try B. We're going to plug the x value in for x, we're going to plug the y value in for y, and we're going to see if that's equal to 6. So we have 2 times 2, 4. Now we're subtracting a negative, which that's the freshman mistake that most people make. Don't make that mistake because you are not freshmen. So 4 plus 2 is 6. So you're saying 6 is 6? True. So 2, negative 2 is on our graph. So true on graph. Let's try one more. 4, 2. So I'm going to plug 4 in for the x value, minus 2 for the y value. Notice that I'm putting parentheses around the numbers that are going in for the variables. That's just to double check that I'm putting each thing in the right spot. So 2 times 4, which is 8, minus 2, is that equal to 6? I believe so. 6 equals 6, true. I like to put check marks by these, and that's going to be on the graph. So 2 out of 3 of these worked. Next up, when we're talking about graphing basic equations, is if we're asked to graph an equation by plotting points, what we're going to do is we're going to create a table. Now, with our table, we're going to get our ordered pairs. So our y-axis, our x-axis, and implied, I know I didn't do this on the last video, but implied is both these lines go off to infinity. So, plotting points. We can start with any number you want. I choose to stick with the easiest numbers, and in general, we're going to hover around the origin for a lot of our basic shapes. And so our independent variable is x, and our dependent variable is y. If we plug in these numbers for x, we're going to get an answer out for y. So, negative 2, which is, and I could write these out like I'm in Algebra 1, but I'm just going to talk you through this. If I plug in negative 2, I get negative 4 plus 5, which is 1. If I plug in negative 1, I get negative 2 plus 5, which is 3. Oh, I already notice a pattern. If I plug in 0, I get 5. If I plug in 1, I'm going to get 7. If I plug in 2, I'm going to get 9. It's going up by 2 every time. Funny how that works. So, I have negative 2, negative 1, 0, 1, 2. And then I'm going to go all the way up to 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm at negative 2, 1, negative 1, 3, 0, 1, 2, 3, 4, 5. My scale is a little bit off, so my line's going to be a little bit off. If I go up another 2, and if I go up another 2. So we can kind of see that my line goes up. So lines, we should be pros at. We're going to do that in the next level. We're going to do everything you should know about lines. But right now we're just starting off easy. So, example 3. Graph this quadratic. We should know what a quadratic looks like. So I'm going to draw my table right here, x, y. I'm going to do the exact same thing. And then I'm going to have my xy coordinate plane over here. Let's get that on the screen. Okay, so if I plug in -2, I get 4. If I plug in -1, I get 1, 0. And this pattern holds. If I plugged in 3 just for fun, I'm going to get 9 because I'm getting all of the squares. This is one of our identity graphs. This is called a parabola, if you don't remember. It's one of those shapes that never escapes you. It's everywhere. If you're watching this and you're by a light, look at the shape that the light makes against the wall. It's a parabola. If you look at the headlights of your car, we get this shape. It's a parabola. If you throw a ball up and then it comes back down, it makes the shape of a parabola. And that's how we do it. If we want to do simply, we can plot the points. All right, moving on to the second page. So a brief walkthrough of some of these terms when we're talking about intercepts. If we're finding the x-intercepts, these are all points on the graph that touch or cross the x-axis. The x-axis is always the horizontal axis. Likewise, if we have y-intercepts, those are all points on the graph that touch or cross the y-axis. So it seems like a basic idea. If it intercepts, it crosses or touches one of our axes. Other than that, those are the only times you'll ever get an intercept. So let's look at this picture right here. It says find all the intercepts on the graph. So we're looking at this. We're going to categorize our x-intercepts. Intercepts. Be nice if I could spell. And y-intercepts. So I'm first going to look horizontally, and then I'm going to look vertically. Each time I find a winner, I'm going to write it down as an ordered pair. So my x-intercepts are at horizontally, I've got 1, 2, 3. So I've got -3, 0. I've got 3/2, 0. And I've got 4.5, 0. Notice what is 0 each time you have an x-intercept. The y is 0. And the y is 0 on the x-axis. Likewise on the y-intercepts, we have, this is going down, 0, 3. Then we also have this 1, 0, -4/3. And we have this last one, 0, -3.5. X-axis, x-intercepts are horizontal. Y-axis, y-intercepts are going to be on the vertical. So what else do you notice here? To find the x-intercepts, we plug 0 in for y. If we have y-intercepts, we plug 0 in for x. So x-intercepts, which is the abbreviation, we're going to plug 0 in for y. And for our y-intercepts, we're going to plug 0 in for x. And then solve from what's remaining. So let's take a look at this next one. Find the x-intercepts and y-intercepts of the graph. So if I want to find my x-intercepts, if I plug 0 in for y, I get 0 equals, because plug 0 in for y. x squared minus 4. Now we have two ways to solve this. We can solve this by factoring, which you guys should remember how to do. It's going to be a conjugate pair because it's the difference of two squares, x plus 2x minus 2, which gives us our zeros of x equals negative 2, x equals positive 2. You could have also solved this by just adding 4. So just as another way, just a little squiggly, if I have the same thing. If I add 4 and I take the square root of both sides, the only trick is when you take the square root of a variable, what we have to remember is to write plus or minus 2. Don't make that freshman mistake of not writing the plus or minus. All right, for our y-intercepts, our y-ints, we're going to plug 0 in for x. So y is there. We have 0 squared minus 4. Well, 0 squared, 0. So we just have y equals negative 4. Now you might have noticed, each way I just wrote the variable. What is missing is we want these to be ordered pairs. So in order to have a full, complete answer, we're going to have negative 2, 0, 2, 0. There's our two ordered pairs. And for our y-intercept, it's going to be 0, negative 4. All right, the next subject is symmetry. And we're going to have 3 different cases for symmetry. If we have something that is x-axis symmetry, that means the shape is the same above and below the x-axis. We are taking the page and folding it from top to bottom. If something has x-axis symmetry, that means it's said to be symmetric with respect to the x-axis, and that's what we're going to look for. Case 2, if you flip it over, if I slide this page in, y-axis symmetry. Something said to be symmetric with respect to the y-axis if I can fold horizontally over, or if we look left to right, everything is symmetric, matches up with our fold line being the y-axis. So if I wanted to try this out, it's not going to work because there's something written on there. If I folded that, they match up exactly horizontally. The last type of symmetry that we talk about is symmetric about the origin. Now I'm going to bring back what we talked about in level 1.1 is symmetric about the origin is things that are symmetrical from the first and the third quadrant. So if I fold over this diagonal, if I get things matching up in these two spots, likewise, I could have symmetry over the second quadrant and the fourth quadrant. I can have a similar fold. And these are all just properties of graphs that we get. If you need help figuring out if something is symmetrical or not, I took this right out of your book. It's called Test for Symmetry. So if you want to figure out if something is symmetrical about the x-axis, replace the y with a negative y. And if they are the exact same thing, then it has symmetry about the x-axis. Likewise, it seems kind of counterintuitive. If I'm looking for x-axis symmetry, I'm looking at the other variable. Likewise, with y-axis symmetry, I'm going to replace the x with a negative x. And then see if these two are going to come out to be equivalent or equal equations. And last thing, with the origin, I'm going to switch both of them. If I have, and if they come out to be equivalent, then they're said to be symmetric about the origin. So let's give this a try and see what happens. All right, so I'm going to use this test that we just went over for example 6. So if I'm going to see if I have x-axis symmetry, because I have no idea what this looks like, I'm going to say, instead of writing y equals this, I'm going to say negative y equals 4x squared over x squared plus 1. Now, these don't look the same. Even if I multiplied both sides by negative 1, to have y on the same side, so I have y equals a negative 4x squared over x squared plus 1. These are not equivalent. They're not the same thing because of this negative sign. Equivalent. So not symmetrical vertically. So with respect to x-axis. And that's, how many words is that to write? 1, 2, 3, 4, 5, 6? That's not that bad. How about y-axis symmetry? So, like it says up here, if I want to see if it's symmetrical about the y-axis or symmetrical left to right, I'm going to plug in a negative x. So I have y equals 4 times negative x squared over negative x squared plus 1. Well, whenever you square a negative, it just becomes a positive. So if I simplify this a little bit, I end up with the exact same thing. So this is, yes, symmetrical about y-axis, which means it maps left to right. And just as a check, origin symmetry, I'm going to replace both. Now, kind of looking ahead, if I plug in a negative for the x, I get the same thing. And if I plug a negative in for the y, I get something different. So, based off the previous work, we can write these 3 dots. This is a fancy way of saying therefore. I always have this conclusion that mathematicians are inherently lazy, so they find out as many different ways of abbreviating stuff as possible. So, based off the previous work, therefore, not symmetrical about the origin. Now, sometimes one of these works, sometimes 2 of these work, sometimes we have a shape that is symmetrical about all 3 of these cases. So we're going to flip the page and move on to the last couple problems. So we're going to be putting everything from this level together, and we're going to be talking about graphing things. We may not know what they look like. So the end product is going to be a graph. So hopefully I have this as straight as possible. I'm going to label my axes. I want to graph the equation y equals x cubed by plotting points. So how do I do that? I got my x, I got my y. What I want to see happen is I want to find out any intercepts from this, and I want to see any symmetry. So what we did normally, and here is the kicker. If I do things that are balanced across the origin, I can automatically check if something is symmetrical. So if I plug in negative 2, I get negative 8, because negative 2 cubed is negative 8. If I plug in negative 1, I get negative 1. If I plug in 0, I get 0. There's our intercepts. So x and y intercepts is going to be at 0, 0. If I plug in 1, I get 1. If I plug in 2, I get 8. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 1, 2. I'm going to plot these points, and then visually I'm going to see if we have any symmetries. So negative 1, negative 1, negative 2, negative 8. So this is the curve that we have. So if we look at this graph, is it symmetrical about the x-axis? If I plugged in a negative y, I am not going to get the same thing back out. Likewise, is this symmetrical about the y-axis? No, Visually, you can tell that it's not symmetrical about the y-axis because it's not the same in these two quadrants. Is it symmetrical about the origin? Well, as we noted, if I plug in a negative y for y, and if I plug in a negative x for x, these should be equivalent statements, right? So if I have a negative y equals a negative x cubed, well, if I multiply both sides by negative 1, I get y equals x cubed, which is what I wanted to from the original. So I've got my x and y intercepts, and I know that it's symmetrical about the origin. So that's kind of the work that I want you guys to proceed with. One more for me, and then the rest of the time you guys have to work. So we're going to graph the equation. Likewise, what I did, there's my xy coordinate plane. There's my x and y table. Now I'm going to plug in variables. So if I plug in numbers, I can't just pick the x value like I did before, because if I pick the x, I'm going to have to solve this. I'm going to have a bunch of work. So instead of picking numbers for the x, I'm going to pick numbers for the y. So for the y, I'm going to pick -2, -1, 0, 1, and 2. And you'll see why in just a second. So if I plug in -2 for y, I get 4 back out. If I plug in -1, I get 1. If I plug in 0, I get 0. If I plug in 1, I get 1 again. If I plug in 2, I get 4 again. Huh. So 1, 2, 3, 4, 1, 2, 1, 2. I have a point at 0, 0, a point at 1, -1, and a point at 1, 1. And I also have a point at 4, 1, and I also have a point at 4, 2, and 4, -2. This is a sideways parabola, and as we go further on, maybe in level 2, we're going to talk about if this is a function or not. But here, the independent variable just as a quick aside, the independent variable here is the y variable and not the x, like every other problem that we've done. So, do we have any intercepts? Yes, we have, just like in the last problem, the x and y intercepts are at 0, 0. And then the last thing is this symmetrical? Is this symmetrical about the x-axis? Yes. I can tell by that visually. If I know how to graph it, I can tell visually. Is this symmetrical about the y-axis? No. And is it symmetrical about the origin? No. So there you have it. That's the completion of level 1-2, and hope to see you again at level 1-3.